Welcome to our talk titled More Interpretable Decision Trees. This is joint work with Eugene Gilmer and Renee Hexel and Vlad Estevil Castro. We'll give a bit of motivation, we'll explain what human in the loop means, we'll mention some earlier systems, then we will introduce parallel coordinates in order to present our algorithm that enables this new type of splits to build interpretable trees. We obtain classifiers that offer a better balance between the size of the tree and the precision of the classification. We will demonstrate this some experimental results and we will finish with some conclusions. Explainable artificial intelligence is the interest we have for artificial intelligence to describe to us in human understandable terms why is a certain classification made. So a system is considered a higher learner. It not only learns, but it can explain to us what it has learned. The original motivation for machine learning was actually to alleviate knowledge elicitation and create expert systems that explain their decision by allowing a human to participate in the learning and steering the learning to a certain objective, probably not necessarily just accuracy, but also interpretability. There are some common approaches to explainable AI, but there's some that argue that it's better from the very beginning to use machine learning models that will be unnaturally understandable. An example is detect which streets need repairs, and unfortunately it alienates low socioeconomic neighborhoods where people do not drive in cars with the system on their mobile phones. Learning decision trees is considered one of the most relevant methods of learning understandable models humans will gain knowledge from and wisdom. All of these algorithms are essentially one single method that recursively builds a decision tree. There have been some earlier systems listed here. Participation of humans is crucial in the selection of the node split. I'll review here some methods that have been used, like steam graphs to visualize a particular training set in order to assist a human to choose a split criterion. There's also circle segments. There's also bar visualization. Perhaps the most dynamic to construct classifiers is WCAS user classifier. Unfortunately, it's not possible to visualize more than two attributes. This is where parallel coordinates come into place. For example, we can explore a data set. A particular case is drawn as a polyline from left to right, where the value on each attribute defines a point on that axis. We can choose highlighted in green a certain range of values. Those values that satisfy that test are used in a node to split the training set. Example of highlighted node, the corresponding test that splits between a large proportion of green cases. With parallel coordinates, we can apply interval tests. These intervals could be finite on both ends, or they could have been an open end. But also we can apply tests that are a rectangle in between two axes. A split in parallel coordinates corresponds to standard one-dimensional range splits in a decision tree. Now the interesting aspect is that if we choose an interval in the middle of two of our attributes, we basically are choosing a diagonal boundary between the concepts with a margin. You'll see an illustration of the effects we can do with the rectangle size to capture a boundary region. Also, parallel coordinates allows us all the same operations with online analytical processing. Here, you see an example of a data set where the human vision sees other patterns that are more discriminatory than the information gain or the Gini ratio. We're suggesting to explore cubes, not just intervals, of parallel coordinates. a test will consist of more than one interval and the corresponding conjunction of them. Our decision trees here will have parallelepiped tests on the nodes of the tree and a decision for a class on the leaves. And the question is if an instance is inside or outside and meets this conjunction of ranges of attributes. We're going to build a volume and we're going to make the number crunching of the machine build this volume by itself. In this case, we are not using human assistance. Now, we also are aiming for very few dimensions to allow for the finished classifier to be transformed in very understandable decision rules. Using conjunctions of attributes does not lose any expressivity. We are introducing a new algorithm. This new algorithm its purpose is just to build a discrimination test of one particular node, and the objective is to minimize the number of attributes used and at the same time minimize the impurity. The way it works is it will start greedily with a singleton interval, and that single interval would be entire range of an attribute and see if that this is discriminatory for a class. That we test for all attributes, and then we try to add all the other attributes to create a volume of size 2. Then once we have the best volume of size 2, we try to build the best box with 3. This iterative procedure will terminate because the best purity is achieved when we use all attributes. Obviously, these algorithms potentially testing all attributes, and for those we are computing the impurity. Although this iterative heuristic is a hill climber, we still want to be more efficient. We also propose a speed up by which we can compute the impurity of a node from previous nodes, because the new node is just the previous node plus some new conjunction. For this, we take advantage of a representation using a bitwise vector. Our software has been organized so that we can even use even 2 integers if we have more than 64 attributes. In the case that we have an impurity that is an instance not of the main class, but still classified, let's say, as class A, and the new test still fails to select the instance, this instance will remain an impurity in the extended volume box. However, if the test does prune this impurity out of that node, we have a new volume, and still our bitwise operation accounts for the total impurity of the new node. It is very optimistic to expect that one attribute or a couple of attributes as a box would be very good classifiers. Our algorithm is not that effective when the full range is not good starting point. So what we do is construct a hybrid approach. If C4.5 produces with one test a better result than our box, we use the test of C4.5. Otherwise, we use the box of the attributes. In this picture, with our algorithm, a much shorter and much more precise decision tree. The leaves are of a pure class, the red class, the yellow class, and the green class. We tested our algorithm in more than 30 data sets of the UC repository, and we use the F1 score to evaluate accuracy, and we also computed the average tree size. The difference in precision between our hybrid, the pure version, and a C4.5 implementation is minimal. We are not sacrificing precision. However, tree size is remarkably better in many cases. In some cases, we don't get such high accuracy, but but our hybrid approach alleviates that. Our code is available online. This paper is motivated by human-in-the-loop learning. However, this procedure is completely automatic. It produces transparent trees, and we can meet multiple objectives like high accuracy and also understandable and comprehensible trees. Thank you very much for your attention.